Hi, everyone, and welcome to the Immersive Streaming Content webinar today. I'm Debbie Fitzgerald. I'm the director in the Advanced Technologies group at Cable Labs, and I'd like to welcome you all today to our second webinar in this series of webinars from the Immersive Digital Experiences Alliance. If you missed it, our first webinar back in October of last year covered an initial prototype of streaming what we call Immersive Technologies media format over an orchestrated edge network. That recording of that webinar is available up on our IDEA website, immersivealliance.org, if you missed it. Since then, several of the engineers within IDEA from Charter Communications, Cable Labs, and OTOY have been working together to advance this to the next level for streaming, and that's what we're here to show you today. Before we dive into this, though, I thought I'd just give a brief overview of IDEA in case this is your first time to an IDEA webinar, and give you a little bit of IDEA's vision. So IDEA was formed to work together to bring immersive media experiences to the masses. In order to do that, the very first thing that we recognize is we need a practical suite of interchange specifications. We want this to be a display agnostic solution. We want it to be able to target both light field displays all the way down to your traditional 2D displays. We want it to be inclusive of 6DoF sound. We don't want to forget sound. That actually is evolving just as quickly as display technologies, and we recognize the importance of that too. We want to be able to deliver this over our commercial networks. That's one of the reasons why Cable Labs actually is very interested in this. We recognize that the payload for light field capture and light field displays can be enormous, way larger than what traditional video compression and video delivery techniques can handle. That is why IDEA was formed, to try to develop specifications to manage the content delivery of this over our networks. And speaking of networks, we're also looking at leveraging what we call media aware networks for efficiency. I'll explain a little bit more about that with this next slide. So we're looking to provide a display agnostic approach, meaning we want to be able to deliver an immersive experience, this rich data to full holographic light field displays, but we don't want to exclude all the other types of displays that will be out there, such as multifocal head-mounted displays, auto stereoscopic displays that are coming out, like from Domenco or Sony. VR and head-mounted displays certainly are taking off with the metaverse, 3D stereo displays, and all the way down to legacy 2D displays. How are we going to do that? We are looking to define the Immersive Technologies media format, ITMF, that will enable the ability to render out the right end video point to deliver to each of these types of displays. I'm not actually going to go into a lot of detail here because Austin Paul is going to discuss more about that later on in this webinar. The purpose of IDEA is, like I said before, to develop a family of royalty-free technical specifications to address the media format and the content delivery. We're also gathering marketplace technical requirements, making sure that we really understand what the needs are out there. Facilitating interoperability, testing, and demonstration. We've actually done that in a number of events already, even before COVID. And produce educational events and materials such as this one. Also to provide a forum for the exchange of information. So that's just a little bit of background on IDEA. I'd like to kick it off to the important part of the webinar today. We've got a number of speakers lined up to demonstrate this to you, starting with Chris Turner, Charter Communications, Kyle Merck from Second Story Data, Abhinav Kashidich from Charter Communications, Austin Paul from Cable Labs, and finally Del Wolfensbarger from Charter Communications. I'm going to turn it over to Chris now. Chris?
Thank you, Debbie. I'm so excited to be here. Hi, everybody. My name is Chris Turner. I'm the Vice President of Emerging Technology here at Charter Communications, and we're super excited to be part of IDEA and what we're going to present to you today. The team I lead here is really responsible for thinking about our technology needs and strategy 3 to 5 years, and in some cases even beyond that ahead. And we go out and look into the ecosystem and what's going on with different partners and try to bring those parts and pieces back in to really enhance either enhance our existing products and services or to bring new products and services to the market. So that's why we're so excited to be part of IDEA. We really think this will help prepare our network and services for the next generation of content. I'm really excited to show you my presentation. So as I said, my team thinks about a lot of new and upcoming use cases for technology and how we can adapt that to work with our existing or new products and services that we want to deploy over our network. So when you think about 3D streaming, this presents a lot of challenges for both service providers and content providers. Things like encoding and decoding this content. Devices are a huge challenge just because they run the gamut from very low-end capability to some that have super high-end capabilities, right? Varying levels of GPU, screen resolution, and you're talking about everything from something like a mobile phone to a high-end HMD. So there's a lot of complexity there when you think about how to transmit 3D content over the network, the bandwidth and latency requirements that we have, and how do we make sure that we meet those. And then even newer display technology like light field displays and next generation HMDs that we expect some of the big players to launch later this year are going to present even more challenges for this technology. So we want to make sure that we provide the highest quality immersive experience we can over the network. And that's what the team at IDEA has been thinking about for quite some time now. So we're going to talk about this new standard called ITMF that the team has been developing. And we're going to hear from Austin Paul, who's really going to get into the nuts and bolts of how this works and what makes it awesome. So take it away, Austin.
Thanks to everybody that's joined the webinar today. Really excited to show this off. And first, what we'll do is we'll give an introduction to the ITMF specification, and then we'll move into the actual demo content. But we think that this is pretty useful background to start with. So ITMF is a royalty-free open source specification. It stands for Immersive Technology Media Format. And it's aimed to the end-to-end support of immersive media content creation, packaging, and network transmission. ITMF is based on the Orbex file format developed by Otoy in collaboration with Mozilla and Autodesk. After its release in 2014, Orbex has been used as an interoperable format in Octane Render and its plugins across 20+ industry digital content creation tools, some of which are available in a free tier for Blender, Daz 3D, Unity, and Unreal Engine. Octane and Orbex are based and extended from the Academy Award-winning book PBRT, designed for photorealistic, physically based rendered scenes. It's the standard file format used across the decentralized rendering network, Render, and the end format of Otoy's light stage captures. The ITMF specification suite is available on IDEA's website and composed of 3 parts: the binary container package, the XML scene graph defining the render node graph system, and data encoding specification designating the scene graph's code points for encoding and decoding. The next version of the ITMF specs are currently under review. So the container is a binary random accessible package utilizing the binary markup language to encapsulate the scene graph, any associated metadata, and all assets within a simple virtual disk system. Its structure is flexible and it supports different encoding structures designed for interoperability and streaming. And it has compression and encryption capabilities for the packaged data and binary encodings. Now, the scene graph, which you're looking at here, provides an XML or JSON representation, offering a feature set to describe a complete, physically accurate synthetic 3D scene based on the PBR node system from Octane. The node graph is very verbose, with numerous node categories covering many different aspects of the scene graph. This diagram here only contains a subset of all of the possible nodes that you can deal with. These categories include things like geometry, volumes, textures, materials, light sources, cameras, and animations. And all of these nodes feed into a render target down on the bottom there that defines rendering settings and the final output. So elements of the scene graph are constituted by many industry-proven formats specializing in the portions of the graph that they cover. ITMF umbrellas these formats as subformats such as OBJ, Alembic, GLTF, and FBX. Those are for geometry, OpenVDB for volumes, and OpenEXR for textures, as well as output for composition. Support for other developing industry standards such as USD and OpenColor IO will soon be supported within the render graph. Any functionality of these subformats is inherited by ITMF. The format also allows extensibility through the use of scripted nodes in both Lua and Open Shading Language, that's OSL. This extensibility, defined with many different node definitions for things like pattern generation and volumetric lighting, provides procedural-driven mechanisms for textures, materials, and geometry. Procedural scene elements can drastically reduce file sizes by providing compute mechanisms rather than data. IDEA is continually improving ITMF while maintaining backwards compatibility to Orbex to include live action capture and hybrid techniques, audio, support for rendering emerging volumetric formats, and interfaces to a heterogeneous array of applications and displays that will provide the means for an immersive experience. So without further ado, I'm going to turn it over to Del Wolfensparger, XR architect at Charter Communications, to demo the stuff that we've been working on.
Thank you, Austin, for that introduction. And I just want to say these are exciting but challenging times for the immersive industry because technology is moving so rapidly. So I'd like to show my presentation to you now, which is going to include a demonstration. As mentioned earlier, we're very excited to share this demonstration with you. We've made a lot of progress since October when we last showed the work that we've been doing, and we've made even more progress since then. So what are we doing? We're streaming the ITMF format directly to Unity and Unreal using a network orchestrator. This network orchestrator is the brains of the streaming itself. By that, I mean, we're using logic, both in the client and on the server, and a Firebase NoSQL database, both on the server and the client, embedded into the client, which can also be embedded into the runtime. We're going to show you exactly how we did this, so let's get started. First of all, we had a tremendous performance optimization by using frustum culling. And what this does is it only renders the frustum, which means what's in the view of the frustum is the only thing that's rendered. All the 3D objects outside of the frustum or the screen itself are not rendered. This allows us to really optimize the GPU rendering that we're doing and be more efficient at rendering as well as delivering assets. A number of other performance improvements were made. Let's talk about them. So by using the GPU and relying more and more on the GPU, we're able to access thousands of threads instead of less threads by only focusing on the CPU. In doing so, we have to recognize that the GPU computational power is improving year over year on both mobile and desktop. So by streaming to the mobile and desktop GPUs directly, we're able to render things into memory much more efficiently than otherwise. Also, we've been working on tweaking our ITMF and JSON translation from the nodes and pins directly to what Unreal and Unity actually need in order to render out the 3D objects and create the scene so that it's a mimic of the scene that was in the original 3D application. We're also doing new things with compression, including Draco, KXT, decimation, which some of the engineers in the project are going to talk about later and explain how they were able to use different optimization techniques to handle network constraints, as well as deliver 3D content more efficiently. We have metrics which we're able to detect at the very beginning of the application launch. So we know what device we're on, we know what the power of the GPU of that device is, as well as the model number and several other things about the device. Once we know that, we can then have the network orchestrator work with the databases that are in the client and the server in order to stream down the correct content from the asset server. So, for instance, if we're using a set-top box like Apple TV, then we send the assets that are specifically optimized for that set-top box. On the other hand, if we're going to a looking glass display, which is a multi-view display, both in 8K and portrait, they have totally different optimizations in terms of the assets that we would send to them. They're totally different from, say, VR or AR. And we do send to those as well. But we can send the exact correct assets that are highly optimized to the device we're on. That's the most important point. And in addition to that, we can actually now create a runtime with the database and the logic embedded in the client so it can talk to the network orchestrator and know where to find the assets on the CDNs, which are located on the network. We're going to explain all this in more detail. So let me run through one last thing, which is that the best analogy for this, I think, is in the early days, there were bitmaps, and then there was vectors. And the vectors were always more efficient. And that's what we're trying to do, find the most efficient way to stream 3D content over the network. And I think we've come a lot closer than we ever have before. Let's talk about speed, because that's so important. When we did the demonstration in October, we were sending a 25 megabyte 3D object in about 55 seconds. Since then, by changing the format of the object and by using compression, we've been able to bring that down to 4.9. And if we go over a 5G or 10G network where we're on the edge basically, and we're bringing the content server or the CDN closer to the actual client itself, we've seen much greater increases, or I should say decreases, in the amount of time that it takes to stream from the server directly to the client. So there's a lot of promise there with further compression and further optimization. Now we're going to look at the actual architecture that we used this time. As you know, we optimized the 3D content. Once we had created the ITMF file, we were able to separate the JSON and the assets from the individual ITMF file, send the assets to the server where they were pre-encoded into these multiple formats, able to send the JSON up to the FileMaker Pro, which we're going to hear about more from Kyle Merck from Second Story Data in a little bit later in the presentation. Once we're there, he's able to export JSON, which goes into our Firebase NoSQL server, which then automatically syncs with the client. And this Firebase NoSQL server is embedded in the Unreal Engine and Unity as well. So either game engine can talk directly to Firebase and know exactly what asset to download. And since we use geolocation, they can know where to download it from, which is vitally important for speed of download. What we're looking at here is the content management system for the Firebase NoSQL database. And if you'll notice, this is the information we're gathering upon the initial launch of the application. So in this case, it was a Apple laptop, M1 Max chip. We were using the Unity game engine, and these are all the parameters that we needed to know. And what you see down below are the actual URLs for accessing the files directly from the network orchestrator, which is sending us to the CDN to get the correct URL for the asset Here we're looking at Octane Render from Otoy. And this is the original scene format. And each one of these is a node, and a pin contains all the camera information, camera position, all the transforms for each individual 3D object, meaning the X, Y, and Z position, rotation, etc. And once we have all this information, this is what's saved off in the ITMF format. And then we use libITMF to actually to convert it correctly to the ITMF file itself, which we can then extract the JSON and the assets from. Here's a scene from the demonstration that you're about to see. And what we've done is we've surfaced the GPU and model information, as well as the frames per second that are running on the device. So this is actually just something you wouldn't see normally, because you would never see behind the scenes when you were watching a demo, or actually when you're watching content. But in this case, since it is a demo, we're showing you what is the frames per second of the device. In this case, it's close to 60. What is the memory allocation? What is the operating system? What is the GPU, the model of the GPU? How much VRAM, which is very important to us, as well as the resolution. One thing I did want to point out is it's kind of ironic that we're showing a 3D streaming presentation by converting it to video and streaming it to you. But I just want to let you know that when we do that, what happens is you're going to see frame drops, you're going to see artifacts, and you'll see banding anywhere that we have gradations. And we have a pretty solid gradation here in this screenshot, and I don't know how well you'd be able to tell how the quality of the original looks like, but I will tell you that the purpose of 3D streaming is to get the highest quality to the user possible. And when you do that by rendering the synthetic content, you don't lose any quality. It can be lossless. Now we do compress, but the render itself can be lossless under the correct conditions. Here we're looking at a matrix of what it would take at 60 frames per second in order to do streaming. And if you look at the looking glass display, you'll see that's an 8K display. It has about 45 views to 100 views, which makes it a multi-view display. And what we've seen is when we try to stream that using the best video compression codecs possible with the optimized settings for quality and speed, we get up into, with H.264, we get up to about 332 megabits per second. And what happens is when you do that, you're putting a tremendous strain on the network, because most networks can't handle that. And so most home networks certainly. And so, we're dealing with a much greater number than we want. And so the way we overcome that is by streaming the 3D, which is actually streaming the individual 3D objects, recreating the scene instead of using pixel-based streaming. And it's much more efficient. And the other thing it does is, though, it gives us the ability to have a much lower bit rate and a much lower file size in terms of total delivery. And to illustrate that, if you look at this slide, you'll see this is not an absolute value here. This is theoretical data transfer rates on the current networks that are available, and also some of the networks that are soon to be available. So if you look at it, the orange line indicates what 332 megabits per second looks like. And as you can tell from this particular chart, that even with the highest networks available, we're still going to run into a bottleneck. So we need to find a way to decrease the bandwidth as well as the total files transferred in order to handle these highly immersive displays, which ask a lot more of us in terms of the actual data being transferred. Now we get to the fun part, the part where we get to show you a demonstration of 3D streaming based on the work that we've described previously and we're about to describe after the demonstration. So we're going to get in more of the how-to in addition to showing you what we've accomplished so far. We think it's a pretty exciting scene. Let's find out. Here we are right after the login, and while the login was happening and the application was launching, we were streaming in all the 3D objects. If you look at the ground down below, you'll be able to see that those are 2 objects which have been replicated throughout the entire scene. And that creates the illusion of well, it's not an illusion really, but hundreds of objects. And I think we have about 500 of these instantiated in memory. All of the 2D displays you see here are actually videos that are being streamed into the display. Notice how the audio changes as we move inside the car. And that has occlusion. We used a JSON audio file that mirrored the file names and also had some parameters for materials and textures. So the materials were metal or glass or cloth, they would have a different sound to them. And all the objects you've seen, including the animations, have all been streamed in. They originally started as an ITMF file with a 3D application called Octane Render. And here we are, once again going inside the car, and again notice the audio changing. Another view, and we're now getting into some of the objects that are animated, and some of them are actually using volumetric effects, which were originally generated with extensions inside of Octane, and then we've simply matched those parameters to the same type of engines inside Unreal and Unity, so that we can do things like have smoke and fire and water and those type of things. Most of these objects are GLTF, or actually GLB, so they have built-in animations. Some of the messages are compressed using compression techniques that we are talking about later on in the presentation from Abhinav and Austin Paul. So here we go. You can see you can do almost anything. I would also point out that the camera moves themselves are all controlled by the user. So these aren't just automated. This was all done by the user, changing the camera moves. So there's really a lot of custom control that the user has because everything is 3D. So we don't actually have to have separate video streams for these different moves. These are all just controlled by the user itself. Coming up, you're going to see how we detect the GPU and the model number of the device. So that'll come up on screen now. And you can see the frame rate of the device is displayed. We detect this upon launch. It happens to be about 60 frames per second because that's what the computer monitor is running at. We also detect RAM, the graphic card, whether it's Direct 3D, what version, what are the capabilities of the device. And then we actually stream the content or the 3D objects into the scene based on what are the device parameters. So up on the server, on the asset server, the network orchestrator knows the capabilities of the device. So the client asks for the individual 3D objects that it needs in the scene based upon what we know about the device from detecting the GPU early on. As you can see, this is a huge area. In fact, in the VR version of this, you can actually go inside the car and kind of drive it all over the place, depending on where you want to go. And hopefully down the road, we'll be able to show you a video of that. But in the meantime, finally, I want to point out is not only is it this giant space, but it's also able to target many different types of GPUs. So we can do mobile, we can do desktop. It just depends on what the parameters are. So we tried to put together something kind of linear to show you that we're not just looping content, but actually showing new content as you drive through. So anyway, thanks for watching the demonstration, and now on to the next part of our presentation. At this time, it's my pleasure to introduce you to Kyle Merck, who's the founder and CEO of Second Story Data. And he's worked diligently on the JSON translation, which we needed to get into Firebase, the NoSQL database. But before I introduce him, I just want to say, I want to thank all of the engineers who helped make this day possible. And we're looking forward to 3D streaming becoming a standard through IDEA. And we thank the IDEA members, the fellow members that we work with who have provided us with consulting and support and direction. So thanks to everyone. Now, before we go on to the next one, I'll remind you once again, Kyle Merck, Second Story Data. Take it away, Kyle.
Thanks, and as he mentioned, I am Kyle Merck, founder and CEO of Second Story Data. Happy to be working with the software engineers at IDEA on this project. With that being said, let's begin. One of the advantages of using the FileMaker platform for this deployment is that not only is it a rapid development platform, it actually very easily handles JSON, making it extremely human readable and easily manipulatable. As you can see here, we get the JSON coming from the export of the ITMF JSON, and we import it directly into FileMaker Pro. From here, we can manipulate it on a per device and per media basis. The advantage of this, not only is it human readable, we don't have to go back to the source file to get new JSON. It also allows us to store just the changes that we're going to make instead of an entire string of JSON. Once we get the JSON ready on a per device basis, we can then export it, and that translated JSON then gets imported into Firebase, where it syncs with the game engine in less than 10 milliseconds. So let's go to the UI that was created. We begin here with our device input. We have a number of devices that we've put in here, and there's a number of features that are used in that device, such as resolution, amount of space, RAM space it uses, as well as where we want these files to ultimately be stored once it syncs with the game engine. Once these devices are in place, we're ready to start beginning to manipulate the media. We bring in each piece of media, and in this case, we're using this Advertis holder JSON that you see right here. And you can see if we go for a very easy, legible piece of JSON that we're now going to manipulate in our next slide. So down here at the bottom is our output section. You see I've grabbed a couple of variables that we desire to translate. In this case, this is our input native value, and they're coming in at some rather large decimal place numbers. So for the Unity engine, I'm going to go ahead and change that to 900. For the Unreal engine, I'm going to go ahead and change that to 1,000. Then using a drop down here for selecting the device that we want to make that translation to, then we can then create a specialized JSON where it imports just those changes for either Unity or Unreal. After doing this on every device, we wind up with a pretty extensive library of what our translated JSON images wind up being. These can then be reviewed on a per device basis, which you can see here as we've translated that X variable from its 9.174 all the way up to its new value. At that point, it then syncs with uploads to Firebase, at which point it then syncs with the game engine and is ready for use. That being said, I'd like to turn this over to Abhinav Kasidic, Senior Engineer of Emerging Technologies, Charter Communications, and Austin Paul, Software Engineer for Immersive Media Experiences Cable Labs. Abhinav?
All right. Thank you, Kyle, for walking us through the ITMF specification and the JSON file. I'm going to present my view on the intelligent buffering. So with this, we introduce a new feature for the ITMF called the intelligent buffering. And what it basically is in a nutshell is that it brings in network awareness while streaming 3D content. So let's get into understanding what intelligent buffering really is, right? So it effectively is defined as when a client, and it fetches 3D assets from a CDN server, whether it's remote or placed at the edge, it's aware of it sends its current network state and compute parameters to the cloud. And when the cloud determines what platform it is at that point, like Del pointed out before, it sends back an ITMF specification, the file itself, to tell the platform what level of detail of the mesh is required, what is the order of fetching those assets from the cloud, etc. And we'll get into more detail of that. Now, so the network awareness is enabled through a cloud orchestration that is running at the back end. And with the objective to minimize the fetch times needed for the clients while streaming 3D assets on different platforms. So we are aware that different platforms will have different render and compute capabilities and existing network conditions. And so intelligent buffering is designed to achieve that purpose of minimizing those fetch times. So how does this all work, right? Like Dell kind of like previously, provided the architecture. I mean, this is a kind of like a stripped down, simpler version of it for us. At the heart of it, intelligent buffering has two components. One, the asset scheduler that sits inside the game engine and contains the logic of fetching the assets in the right order. But the question is, who decides that order and how is that provided? And there comes the second part of intelligent buffering called a network orchestrator. So how this would work is it can be broken down into three major steps. Step one, the client updates its network and compute parameters to the network orchestrator. Upon receiving that information from the orchestrator, it determines the asset LOD, compression, and the fetch order for different assets. And then it bundles that thing into an ITMF container that contains the reference to multiple versions of the 3D assets. Now, those 3D asset versions could include compression levels, decimation of meshes, like Del said before. How Kyle has described previously, the ITMF container has different parameters for the device that is transferred back to the client. So once the client is aware and knows the order in which they need to be pulled, it finally makes a call to the asset server at the CDN. We can place it on edge for better latency here. So the client fetches these optimal 3D asset versions from CDN servers, and that pretty much completes the basic fundamental working of network of intelligent buffering. And so let's take a deeper dive into the asset scheduling and compression, because this is important. The ITMF container, when it's sent back from the orchestrator to the client into the scheduler, the order is created by network conditions and compute capability. At this point, the network conditions would include just the latency and the bandwidth at that point, and the compute capability includes CPU, GPU memories, even number of cores. We have limited our scope to just latency, bandwidth, and CPU memory at this point in the ITMF container. Once the asset scheduler knows and has the ITMF container, it then uses that container to make fetch calls to the CDN servers. Now, these CDN servers will have assets of different versions, and by versions, I have used a global terminological version that encompasses mesh compression and texture compression, which also includes image compression also. And the goal of fetch call is to minimize the overall visual experience to a user, right? So we do want the fetch calls to come in the memory. Like, again, if you refer back to Dell's frustum culling slide, you would see that it's only the things that are in view that are supposed to be there at that point, and that's why the fetch call is important. The asset version, of course, would try and have a kind of a compressed file depending on the existing network conditions, and so that should have a minimal impact on the visual quality. Now, to see how all of this works, let me try and run a small clip through this, in which I make on Unreal Engine on Windows box, I make a call to a server and fetches these assets. And it kind of like spawns also and clones also multiple instances of an asset. And this pretty much has the advantage of fetching it once and reusing it multiple times for multiple scenes. So now that it sits there, it can be fetched once and reused multiple times. The other part, as we demonstrated with this clip, is that it was aware of the network conditions at that point. We had the order in which these assets were to be fetched stacked up already from before. And that was provided by the network orchestrator. Different platforms will have different orders and different versions of these of the content. So, if it's mobile, then it has to be a more compressed image. Not everything needs to be there, versus VR that could have perhaps different resolutions. And if it's computer or PC, PC or Mac, it'll have, again, a different kind of asset versions for it. So that pretty much, encompasses the idea behind intelligent buffering demo. But that's not all to it. I think we've gone further and, got some metrics. And the metrics dashboard actually presents the actual technicalities and technical measurements, which Austin Paul from Cable Labs would now show in his slides. So Austin, over to you.
Yeah, we've got a lot that we want to cover, so I'm going to do my best to get through it promptly, but we'll see how it goes. So, all right, I'll get right into it. So, as Abhinav explained, having rich network awareness is critical to enable effective intelligent buffering. So for this reason, we've instrumented our system to gather various metrics into a dashboard, which is shown here. We'll only present a few plots today for the sake of time, but I'll talk through each of them one at a time to illustrate some of the important takeaways and characterize some of the data flows associated with asset transmission. So one of the major advantages of intelligent buffering is that assets can be delivered using a CDN deployment, bringing with it many well-known advantages like reliability, performance, and scalability. So all of the business logic can be consolidated on the client and the network orchestrator. For interactive use cases, which are particularly sensitive to latency, such as cloud gaming and various ideas related to the metaverse, we can deploy orchestrators within a few hundred miles of target clients to maintain low latency. Now I'll move on to the next graph. So this plot presents two metrics side by side for various assets. Bandwidth, which is denoted by the gray bars with the axis on top in megabits per second, and latency in milliseconds, denoted by the orange and red bars with the axis on the bottom. These data points were measured at runtime during that 3D stream clip that Abhinav presented earlier. So in intelligent buffering, bandwidth and latency are some of the most important metrics to consider when making asset scheduling decisions in real time. So we also try to illustrate a basic approach to the scheduling problem here. The vertical dashed line that you see on the plot signifies a latency threshold. If we observe an asset was transferred with a latency above 45 milliseconds, then we toggle on a high latency mode where assets with lower levels of detail are selected. This is just a simple example algorithm, but you could think of this as a very early analog to adaptive bitrate streaming in the 2D world. Essentially, your goal is to deliver the best quality content possible under the network conditions that exist for the client. In this case, we can do so without actually adjusting the pixel resolution of the content. Instead, we're adjusting texture and mesh size, whose impacts can usually be quite subtle. So this waterfall plot shows a trace of asset transmission over time during a short 3D stream. You can see that assets 0 and 1 were transmitted concurrently. Then assets 2, 3, and 4 came after that. This is effectively how we'll evaluate the performance of intelligent buffering algorithms with two main criteria. The first is asset availability. We need to ensure that assets are present and ready to render on the client for the entire duration that they're present in the scene being streamed. That's why, for example, it might be best to ensure that assets 0 and 1 are transmitted before anything else if those two assets appear first in the scene. The second criteria that we're looking at is transmission time. Essentially, you can imagine that we want to minimize the horizontal length of this graph, which corresponds to the total time spent transmitting all of the assets. So if you're following our progress, we're pretty sure that you're going to see more variations of this plot in the future as we implement more advanced algorithms in intelligent buffering. So on this plot, we compare traditional video streaming, which we call 2D here, and 3D streaming in terms of bytes transferred every second. Just for illustrative purposes, we're not doing a lot of a huge scene right here. Each of them transfer about 40 megabytes of data in total in this trace that you're looking at. And the 2D video is just 1080p H.264. So as you can see, the 3D stream transfers everything in one big burst up front, while the 2D stream transfers video frames steadily over the entire duration of the content playback. So to be clear, what we're trying to say is that 3D streaming is an important tool in the toolkit of conveying immersive media. And what we want to do is kind of explore some of the different things that 2D and 3D streaming respectively excel at. So first, from a creative standpoint, barring any subtleties about color profiles and DPI and the like, you can pretty much say that 2D video is what you see is what you get. A 2D video is essentially going to look the same on my computer monitor and yours. Sure. If we're only distributing content to standard 2D displays, that's easy enough. But if we want to distribute to 2D displays and VR headsets and holographic displays, for example, there's a lot of new questions that arise. So how many new versions of the content do I need to produce? How can I guarantee that everybody gets good quality of experience when some users have 6 degrees of freedom in a VR headset and other users might have a flat, non-interactive video in front of them? This is much easier to control for in a scene graph, where you can manipulate the individual assets and meshes and textures and cameras than you can in a 2D video file. So we say that 3D streaming simplifies this process by cutting out an extra step. So as we've discussed in the past, the bitrate requirements to serve 2D streams on today's display resolutions are generally well supported by modern network infrastructure. But it's when you start to consider future holographic displays and higher end AR and VR applications that this falls apart. In particular, future full parallax holographic displays are expected to require essentially 2 orders of magnitude more pixel equivalents than 2D displays, which is tremendous. 3D streaming effectively sidesteps the problem by transmitting assets instead of video frames. So finally, 3D streaming is unlikely to perform better than 2D streaming on particularly short content. The difference is most visible when you have scenes that last for tens of seconds or more, because that means that we get to enjoy more asset reuse, which means less network chatter, as you can see in this example plot where the 3D stream kind of gets quiet after the first 5 seconds. So the longer term goal on our roadmap is to see if we can do what we call split rendering. And by that, what we mean is mixing 2D and 3D streaming to provide the best possible quality of service for every client. So if you're curious, we discussed this in a bit more detail in our October 2021 webinar, which you can find on this link right here. So to conclude, all of these metrics come together to make a really broad design space to find the best possible solution for the job of presenting immersive media over the network. This has been just a little glimpse, but we're looking forward to showing you more in the near future. So thank you so much. And with that said, I'll turn it over to Del to lead the Q&A. We're opening it up for questions for any of the presenters at this point.
Thanks, Austin. That was a great presentation. And if you have any questions, feel free to type them into the chat window directly for Q&A, and we will attempt to answer them for you. So we've had a number of questions before. So let's, one of them was network constraints. So Abhinav, I know you were working on that. So do you want to answer that about what happens when network constraints come into play when you're 3D streaming?
Sure, Dil, absolutely. We can go with that. So when I said network constraints, we have limited our scope right now to just latency and bandwidth. And so what happens is the client sends an HTTP based a message to the network orchestrator to kind of get a round trip time from the backend, right? And we do that at the start of fetching different assets. Now, this could go two ways. One could be that we could first, before streaming any asset, we could just check the RTT and then have a fetch call made to the CDN. We could also, to speed up things, lock in as a state of, like, let's say, we measure the last in the last few milliseconds that it was kind of low latency situation. Then we don't even have to check with the network. We can just cache that information for a while and then use that to fetch the content. So that's one of the ways. And when the first asset gets downloaded or downstream, we measure how much of throughput went through in a given time. And if the download conditions were strong, then we have the confidence to move ahead and get more higher quality assets. And that happens. So the download speed for the first asset would influence how the second asset should be fetched and so on. So that pretty much is like at least the basic implementation to start with of these network conditions that exist at that point.
Thank you, Abhinav. Another question that came up was, what is the actual latency between the database and the server and the client? And I'll answer that. It's typically single millisecond. It's extremely, not single millisecond, it's single digit millisecond. So it's typically under 10 milliseconds. And it's a very small payload because we're actually just sending JSON. So it's text-based. So typically that's not a problem. And we've kind of measured it and seen 2, 3, 5, 6 milliseconds in terms of the database communication. One thing I will add to that is once the initial run has taken place and the database is actually populated at the client, if there was a problem connecting to the database in the future, it uses the local version of the previous data that it's got. And also by keeping everything in the database, we can actually use the same client and repopulate it with different assets. So that's something to consider too for databases. And any other questions we have here? I see we have someone asking if we could stream 2D video along with 3D. Austin, could you answer that?
Yeah, so that kind of goes back to what we were talking about with split rendering in our October webinar. So essentially what we would want to be able to define is a way to dynamically decide, okay, this portion of our scene we want to 3D stream to the client and render on the client. And then the rest of the scene we would want to stream as a kind of 2D video. And then we can merge those together at runtime to get kind of the end result that's viewed by the viewer. And the thing that's really exciting about that, if we can get that dynamic split, is being able to kind of target or tailor your quality of service to the specific hardware situation and the specific network conditions that every individual client is facing. So that's kind of what we're looking at there, if that answers the question.
I think it does, Austin. Thank you for that. Some people are suggesting that they want to know if it will actually run on different devices and if there's any limitation to that. So I don't believe there is actually, but let's see if Abhinav, do you want to answer that?
Most certainly, Dale. Since we tested out this on Unreal and Unity both, Dale was on Unity side, I was on Austin and on Unreal side. Whatever kind of works with Unreal, the devices that could work with Unreal Engine, they'll be supported. For this test, at least we did Oculus, Mac, and Windows platform. We could extend easily to mobile devices, although it'll be a little bit compute heavy. But that pretty much outlines the scope of application. And that would also include the looking glass and light fields.
Someone asked, is WebGL a possibility? And absolutely, because the game engines themselves will target WebGL as a platform. And so you could certainly stream to WebGL as well. So.
All right, thank you. Thank you. We're at the top of the hour right now, so I need to wrap this up. I just wanted to bring everyone's attention back to our website, immersivealliance.org. We will make this presentation available online, and we will let everybody know when that is available. Also, there were a few questions that were asked in the Q&A chat box and answered in the Q&A chat box. So if you didn't catch that, you can look over at those that discussion right now. And again, I thank you all for your time. I thank all the speakers for their amazing presentations today. And we'll conclude with that. Thank you.